In this video, we're going to be talking through our practice problems related to Dalton's law of partial pressures. Okay, so again, info about that law can be found on slides 27 and 29. This video is going to be a little bit longer just because I want to work through all of the partial pressure questions just all in one take. So the first partial pressures question comes along on slide number 28. And in this problem, we are given a mixture of oxygen and chlorine gas. Partial pressures are 104 and 93.6 millimeters of mercury, respectively. What's the total pressure? Okay, so here we're using that first concept from Dalton's law, right? And that concept is that the total pressure in a system with a mixture of gases is equal to the sum of the partial pressures of each gas in that mixture. Okay. So in this question, right, we're given that the partial pressure of oxygen gas is 104 millimeters of mercury. Okay, and then we're given that the partial pressure of our chlorine gas is 93.6 millimeters of mercury. Okay, so there's kind of two ways to do this, right, because they want the total pressure. In atmospheres, you could add them together and then convert, or you could convert them each to atmospheres separately and then add them. Okay, I'm going to do the former of those two choices because it only involves one conversion. Okay, so it's going to be a little bit easier. So, and I'm not going to round for sig figs until the end here. Okay, but we get our total pressure. It's going to be the sum of those two partial pressures, right? So it would be 104 plus 93.6. And when you plug that in your calculator, you're going to get 197.6 millimeters of mercury. Okay, and then I'm going to want to convert that to atmospheres. So to do that, I'm going to set up my T-chart. Okay, and we remember that 1 ATM is equal to 760 millimeters of mercury. Okay, and when you rock that algebra, you get 0.260 ATMs. Now, why did I round to 3 sig figs? Well, even though this one had 4. Well, think about this. If you followed the addition sig fig rule, right, you would cut this off at the ones place, right? You would cut this off, round it up to the nearest whole number. So that really would be 3 sig figs here. So we want to round our final answer to 3 sig figs. Okay. So that first one was pretty straightforward. Okay, then on slide number 30, we get another one. Okay, and in this problem, we're kind of asked to do the opposite. We are given the partial pressures, or I'm sorry, we're not given the partial pressures. We have to find the partial pressures. We're given the total pressure. Okay, so we know that our total pressure in this question is equal to 3.75 atmospheres. Okay, and what else do we know? Well, we know we've got 3 moles of nitrogen gas and 4 moles of hydrogen gas. Okay, and we want to know what are those partial pressures. Okay, so this is getting to kind of the second half of Dalton's law, okay, which is that the partial pressure of a gas is equivalent to the mole fraction, okay, which is just the moles of that gas divided by the total number of moles present in the mixture, okay, multiplied by the total pressure. Okay, so we're going to need to use this equation for nitrogen and then for hydrogen. Okay, so our partial pressure of our nitrogen gas is going to be equal to, well, how many moles of nitrogen gas do we have? We've got 3 divided by, what's the total number of moles here? Well, the total number of moles is 7, right? 3 moles of nitrogen, 4 moles of hydrogen. So that's our mole fraction of nitrogen gas, and we would take that and multiply that by our total pressure, which we have been told is 3.75 ATM. Okay, and when you do this calculation, I'm not going to be too picky about sig figs here, right? Because you could argue that's one significant figure, or you could argue that's a counted value. Okay, I'm not going to worry about it. We're just going to round it to 3 sig figs. Okay, so when you do this algebra and you get your answer rounded to 3 sig figs, we get 1.61 atmospheres is the partial pressure of nitrogen gas, and then we would do a very similar setup for hydrogen gas, right? The partial pressure for hydrogen gas is going to be equal to 4 moles of hydrogen over, again, 7 moles total of gas in that mixture. Okay, multiply by the total pressure, which is 3.75 atmospheres. Do that again, round it to 3 sig figs, you get 2.14 ATMs is the partial pressure for our hydrogen. Okay, and if you ever want to double check yourselves on these, think about it. What should your 2 partial pressures add up to? Well, they should add up to your total pressure. Okay, so do a quick verification in your head. These 2 numbers added together do, in fact, give us 3.75 atmospheres. Okay, we're given a similar problem on slide number 31, where we're given the total pressure and asked to find the partial pressures. Okay, but this time they tell us the percent composition of the gas mixture. Okay, so it's telling us that we've got 45.0% of this gas mixture is neon gas. Okay, and the rest we are told is helium. Okay, and then it tells us that the total pressure is 6 ATMs. Okay, so real quick, we can easily figure out what percentage must be helium gas, right? If 45% is neon, that means the remaining 55% of that gas composition must be helium gas. Okay, now we need to think kind of back to this formula that we used up in the previous problem. Okay, here we were given a mole fraction, right? We were given the amount of moles of each gas, and we could find the total moles of gas present. Okay, here, instead of a mole fraction, we're given percent composition. Okay, so think back, we did some of this in chapter 6. Okay, when you're given mole composition, you can figure out, when you're given percent composition, you can figure out moles by imagining, what if you had 100 grams of this gas? Okay, so if you had 100 grams of gas, you could figure out how many moles of each of these gases you had, right? Let's say you had 45, right? If 45% of it is neon, it's 45% neon by volume. Abandon. Ignore what I was just saying about, I was confused, you guys. I apologize. I thought it was 45% by mass. If it's 45% neon by volume, that means that 45% of those collisions contributing to the pressure are coming from neon. Okay, so neon is contributing to 45% of our total pressure. Okay, or the mole fraction of neon would be 45 over 100. Okay, I apologize. My brain went off on a tangent. I've been recording a lot of videos lately, and it gets really hard talking to myself all day. Okay, so if we wanted to find the partial pressure of neon, we would say, well, what is 45%? That's the same as a fraction of 45 over 100, or our mole fraction. Okay, times our total pressure. And we would get that the partial pressure of neon is 2.70 atmospheres. Again, just round this off at 3 sig figs. Okay, and if we did a similar process for our helium, right, we would get that the helium, that mole fraction would be 55 out of 100 times our total pressure. And you do that, you round it to 3 sig figs, and you get 3.3 atmospheres. Okay, do a quick check. Do my partial pressures add up to my total pressure? They do. We are good to go. Okay, one more problem. Okay, our last gas law problem comes up on slide number 32. And this is more of an AP style question, okay? So this is going to require a little bit deeper thinking, but let's kind of read through what's happening. So 2 flasks at the same temperature are joined together by a glass tube with a stopcock, okay? Let's kind of draw what that's going to look like. So we're going to have 2 containers with gases, okay, and they're joined together by a tube, a glass tube. Okay, and in this tube we have what we call a stopcock. You guys, that's a fancy word for a valve. Okay, so it's a valve with a little like kind of hole in the middle, and you can twist the valve to turn it on or off, and you can either allow the gases in these chambers to be separate if that valve is off, okay, or the gases can flow back and forth between both chambers and mix together if the valve is open. Okay, flask A, we'll call this A. We'll call this flask B. Okay, flask A has a volume of 3.5 liters and contains oxygen gas. So we've got oxygen gas in there at a pressure of 3.25 atmospheres. Okay, in flask B, our volume is 4 liters. Okay, we're working with, I believe, carbon dioxide. Okay, and that's at a partial pressure of 2.75 atmospheres. Okay, and the question wants to know, initially they're held separately. Okay, then we're going to open up this valve here and allow both gases to mix together. Okay, what will the final total pressure be? Okay, so we kind of can figure out, right, that at the end of this problem, we're going to have a mixture of gases, and we're going to be dealing with Dalton's law of partial pressures. Okay, but I want us to think, what other gas law do we need to consider to solve this problem? Well, let's think about it, right? We have these gases held separately. We know their volume and we know their pressure. Okay, the temperature is not changing here, right? Or if it does, it's going to change equally for both gases, so it's kind of irrelevant. Okay, we're not adding or removing any more gas here. Okay, so the only 2 variables that are really going to change is the volume and the pressure, right? Because let's just think about oxygen by itself. Right now it's at 3.5 liters. When you open this valve, now this oxygen is allowed to occupy both chambers of gas, right? So for our oxygen, here's what's going on. We know we have 3.5 liters at 3.25 atmospheres, and when we open that valve, we're changing our volume. We're going to be increasing our volume to, what's the total volume here? 3.5 plus 4 liters in this chamber. We're increasing our volume to 7.5 liters. Okay, what is this looking like? Well, you know that if your volume increases, what's going to happen to your pressure? Well, it's going to decrease, right? And that's Boyle's law. Okay, and we have the same situation going on for carbon dioxide here, right? Carbon dioxide is initially 4 liters and 2.75 atmospheres. Again, when you open that valve, your carbon dioxide is going to be able to flow between both chambers. Okay, so carbon dioxide's final volume will also be 7.5 liters. Okay, they're just mixing together, but the amount of volume that they're each occupying is increasing when you open up that valve. Okay, so again, for carbon dioxide, we want to know what's the pressure that gas is going to have in the final system. Okay, so you can see this looks like Boyle's law, and this also looks like Boyle's law. Okay, so if you were to set this up, you could find the final pressures, okay? Or the final partial pressures, right? Because then we'll have a mixture. So our partial pressure of our oxygen gas, okay, we're going to be using some Boyle's law here. Get your P1, V1 equals P2, V2. And if you rock your algebra, you get that the partial pressure of oxygen will be 1.52 atmospheres. And the partial pressure for carbon dioxide, set up Boyle's law, P1, V1 equals P2, V2. Okay, and if you rack your algebra, that second pressure of carbon dioxide will be 1.47 atmospheres. Okay, so those are the partial pressures, right? Once those gases mix in the 7.5 liters worth of space. Okay, and you know, according to Dalton's law, that if you add those two values together, you get your total pressure. In this case, it is equal to 2.99 atmospheres. Okay, so you guys, that is it for chapter 13. Next, we're going to move on and start talking about liquids and solids a little bit, and hopefully by then we'll be able to return back to school and see each other. So I'll know more about that shortly. Okay, stay safe.